Hello there. Hello. Get started in about 1 minute here. Okay, I'm going to go ahead and get started. Hope everyone had a good weekend. I had not so great weekend just because I had a lot of papers to grade for IB, and it's just not very fun. But I'm one step closer to having them all finished, so that makes me happy. So let's go ahead and get started. So this is CHL 322, period 7. All right, so last time, what we discussed was the effect of magnetic fields on charged particles. Okay, and so there were, so we learned basically the rule for the magnetic force, and it's Q times V cross B. And so this full vector form of the force is not really used until you get to higher level physics. And so at our level, what we're going to use most of the time is the formula for the magnitude of the magnetic force. Okay. Okay. Which is magnitude of the charge times magnitude of the velocity, also known as the speed, times magnitude of the magnetic field times sine of the angle between the two. Okay? And then to get the direction, we use the right-hand rule or the left-hand rule if you have a negatively charged particle. All right. And then what we talked about is how the magnetic field causes charges to move in circles. Or in the more general case, in like spiral shapes, helixes. Not a spiral, because a spiral curls in, but a helix. And we found that the radius of that circle is mv over qb. This is absolute value of q. And then we also talked about how the magnetic force does no work which means basically it can't change the speed of the particle. All right. Which means that it can only redirect. All right, so these are all things that yeah. And this is only when acting on a single particle. Okay, so it can do things like push around extended objects, but with a single particle, it can only redirect it. All right, so that was last time. And so today, we are going to learn. So last time we assumed that the magnetic field was given. And then this time what we're going to do is learn how to calculate the magnetic field. So how does the magnetic field have the value that it has? All right. And so the law that tells you how to calculate the magnetic field is called the Biot-Savart law. I'm not sure if that's one person with a hyphenated name or two people, to be honest. Biot-Savart law. It's a French person or people. So yeah, it ends with T's. Both words end with T, but you say it like there was no T. Biot-Savart. Okay, don't sound like a bozo and say Biot-Savart or something like that. Or as I like to call it, the BS law. But basically what it is the Coulomb's law. Only for magnetism. All right. So if you recall, Coulomb's law is the law that tells you how to get the electric field from a charge. The Biot-Savart law is how to get the magnetic field from some charges. Okay. So what causes magnetism? Well, it turns out that electric current, I, is the source of magnetism. Okay, so electric current, you might recall, is the flow of electric charge. So you have to have moving charge is what creates magnetic fields. Okay, if all the charges are stationary, then you don't have any magnetic field present. But if the charge is moving, then you get a magnetic field. And so, as I said in the last lesson, cross products appear all the time in magnetism. Okay. And so I wanted to just do a quick review of cross product. So let's say you have A cross B. The magnitude of the cross product, just like up here, is the magnitude of the first vector times the magnitude of the second vector times the sine of the angle between them. Okay? And to get the direction of the cross product, you use the right-hand rule. So basically, you take your right hand and you put your pointer finger with the first vector. You put your middle finger with the second vector. And then your thumb is with the direction of A cross B. All right. So with cross products, it matters the order the cross product is in. So A cross B is not the same thing as B cross A. In fact, they're opposites of each other. Because you can imagine if you have your pointer finger going up and your middle finger going to the right, if I put, then that leads to a cross product that is back towards the wall behind me. Okay, but if I put my pointer finger to the right and my middle finger up, that leads to a cross product that's towards the camera. So whereas regular multiplication is commutative, like 3 times 4 is equal to 4 times 3, the cross product is anti-commutative, meaning that A cross B is equal to negative B cross A. All right, so it's a little bit different from the regular rules for multiplication. All right, and so the next thing I wanted to talk about is something called the DL vector. Okay, and the DL vector, it points tangent to a wire in the direction of current flow. Okay, so let's suppose I have a wire that is kind of like this, maybe. It's a bendy piece of wire. Okay. And so if I looked at, I don't know, this tiny segment of it, the current is flowing in that direction, so it points, the DL vector points tangent to the wire. Okay. How about right here? The DL vector points tangent to the wire in the direction of current flow. What about right here? The DL vector points tangent to the wire in the direction of current flow. Okay, so no matter where you are along the wire, it points tangent to the wire in the direction of current flow. The magnitude of DL vector is usually written as just DL without the arrow, and it is equal to the length of tiny segment of the wire. Okay, so however long this segment is, it's going to be an infinitesimally small segment. It's the length of that. All right, and then we also have another vector called r hat, and r hat is a unit vector. And remember, unit vectors, they have a length of 1. So unit vectors have a length of 1. And r hat points from the segment of wire towards where we want to calculate the magnetic field. Okay, so let's suppose that we wanted to calculate the magnetic field right here at point P. Okay, then the r hat vector would point in that direction for that segment of wire. for this segment of wire, it's going to point, r hat is going to point in that direction. And then for this segment of wire, r hat is going to point in that direction. Okay, so it points towards where we want to calculate the magnetic field. And then lastly, we have just the variable r, and that is the distance from the segment of wire to the point P. So for example, if I was looking at this segment of wire, then I would measure this distance right here, that straight line distance, and that would be r. Okay? So now we have all the pieces that we need to assemble in order to state the Biot-Savart law. All right? So the Biot-Savart law is equal, it tells you the magnetic field is equal to mu naught I over 4 pi times the integral of dl crossed with r hat over r squared. All right. So this r is the same r that appears right here. This r hat is the same r hat that appears right here. This dl vector is the same dl vector that appears right here. Okay. I is the variable for electric current. Okay. So why it's an integral, why is it written with a circle? It's because wires are typically loops. They're part of an electric circuit. Okay. And if you cut the wire, then you have stopped the electric current flow. So if there is current flowing, then there's going to be a loop of wire. And so to indicate that it's a loop, you put the circle here. All right. So this is the Biot-Savart law. All right. Mu naught is a constant, and it is called the permeability of free space. Okay. And it's kind of a constant of nature. It's more of an artifact of the units that we have chosen to use when we're doing physics. Okay, and you'll see why just right now, because the value of mu naught is 4 pi times 10 to the minus 7, exactly Tesla meters per amp. So it's kind of like a, it's like an artificial constant that's just there because of the units. All right. I want to contrast that with epsilon naught, which is the permittivity of free space. All right. So there's the permittivity of free space, and there's the permeability of free space. And they're not really independent of each other. Okay, they're just artifacts of the units that we've chosen. Here's a fun fact. What if we did 1 over mu naught times epsilon naught, and then we took the square root of that? Okay. So that would be square root of 1 divided by 4 pi times 10 to the minus 7 times the value of epsilon naught, which is 8.85 times 10 to the negative 12. Took the square root of that. So let's see what happens if I plug that into my calculator. So I've got 4 times pi times 10 to the minus 7 times 8.85 times 10 to the minus 12. Okay, now I have to do 1 over that, and then I have to do square root of that. And I get, let's see, this is like 2.99 times 10 to the 8th. That's about 3 times 10 to the 8th. And if you worked out the units, that would be meters per second. And this is the speed of light. Okay? So really, the constant that appears in Coulomb's law and in the Biot-Savart law is really just the speed of light, or is a speed of light multiplied by square root and all that stuff. Okay, so really there's only one constant here. It's just the speed of light, and mu naught and epsilon naught are sort of like constants that are representing the relative strengths of electric and magnetic fields. So this is actually, back in the, I think it was late 1800s, we didn't know what light was, okay? And so what happened was a pretty accurate experiment was done that actually determined the speed of light. So they said there's this wave, it's called light, and it travels at 3 times 10 to the 8th meters per second. The guy's name who determined the speed of light, his name was Fizeau. So you can look up Fizeau. So he was the first person to measure the speed of light using a pretty ingenious method of like spinning gears, and I don't know. I don't even fully understand it. But anyways, he calculated that the speed of light is that. Okay. Then there was this guy named James Clerk Maxwell who wrote down all of the laws of electricity and magnetism. So he was the first guy to take electricity and magnetism and take all the laws together and write them. There's actually 4 equations of electricity and magnetism, and they're called Maxwell's equations. And so James Clerk Maxwell took those 4 equations and he was able to combine them to show that the electric and magnetic fields can make waves called electromagnetic waves, okay? And the speed of those electromagnetic waves was square root of 1 over mu naught times epsilon naught, okay? And so he calculated that, and he got 3 times 10 to the 8th meters per second, which was the same as Fizeau's experimental calculation of the speed of light, okay? And then so Maxwell was the first person to make the connection that light is an electromagnetic wave. Okay? And so that was purely a guess based on the fact that Fizeau's experiment of the speed of light resulted in a speed that was the same as his own calculation of the speed of electromagnetic waves. Pretty cool. And then further experiments showed that, that wasn't in fact the case. So what we're going to do for the rest of this lesson is today we're going to talk about circular loops of current. Okay? And then in the next lesson, we'll talk about lines of current, straight wires carrying current. So what if we have a circular loop of current? Here's the center. That circular loop has a radius big R. And there's current going around this loop in the counterclockwise sense. All right. And so we would like to calculate the magnetic field at the center of the loop. Okay. So let's just pick out a segment of this loop of wire that's carrying current. Then its DL is going to point tangent to the circle in the direction of current flow. And as I said, DL is, or as I said, the current is going around counterclockwise. And then the R hat vector is going to point towards the center of the circle. And these two are making right angles. Why does R hat point towards the center of the circle? It's because that's where we want to calculate the magnetic field. Okay. If we had chosen a different segment of wire, like maybe right here, we have DL points tangent, R hat points towards the center. Okay. So that's how that works. So let's figure out what is DL cross R hat. Okay, that's always the first part of a Biot-Savart problem because you can see that it involves the integral of DL cross R hat over R squared. Okay, so we got to figure out what DL cross R hat is. So first, let's get the magnitude. So the magnitude of DL vector cross R hat is going to be the magnitude of the DL vector times the magnitude of R hat times the sine of the angle between them. Now, what is the angle between them? Well, because of the geometry of the situation, the angle between them is 90 degrees. The sine of 90 degrees is 1. The magnitude of R hat is 1 because it's a unit vector. And the magnitude of DL vector is just DL with no arrow over the top. Okay? So the magnitude of DL cross R hat is just going to be DL. All right? For the direction, again, so this is we're using the right-hand rule, okay? So I put my pointer finger in the direction of DL, okay? And then keeping my pointer finger like that, I put my middle finger in the direction of R hat. So you can see that I've got that correct. You can see the DL. See, that's the perfect vantage point for you to see that I have it done correctly. And then my thumb points out of the page. So out of the page in the Z hat direction. So Z hat is what we're going to call out of the page. All right? So putting that together, so any vector can be written as its magnitude times its direction vector. So that means that DL cross R hat is equal to its magnitude, which is DL with no arrow, times its direction vector, which is Z hat. All right? So we're going to be using that. And then the other thing I want to point out is that R, or little r squared, is the distance of the segment of wire from where we're calculating the magnetic field. And because the wire makes a circle, this segment of wire is a distance big R from the center. So little r squared is equal to big R squared, which is just a constant. Every segment of wire is the same distance away from the center of the circle. If we wanted to calculate it off-center, that wouldn't be the case. Okay? So now what we do is we just plug in to the Biot-Savart law. Okay? So the magnetic field at the center of the circle is going to be mu naught I over 4 pi times the integral around the loop, because it's a loop of current, of dl cross r hat over r squared. Okay? So now I'm going to plug in the various things that I just figured out here, okay? So for dl cross r hat, I'm going to plug in dl magnitude times z. For little r squared, I'm going to plug in the constant big R squared. All right? So z hat vector is a constant. It always points out of the page. By the way, it doesn't matter which segment I choose. You can show that no matter where you are in the circle, it always points out of the page. Okay? So let me do this one, for example. What if I had chosen this segment? Then I have dl goes this way, r hat goes this way. My thumb is still out of the page. It doesn't matter where I am in the circle. It's always out of the page. So the direction is constant and the r value is constant, so I can factor those out. So I have mu naught I z hat over 4 pi r squared times the integral of dl magnitude. Okay, so what is this integral of dl magnitude? What does it mean? This is the sum, because remember, all integrals are just sums. This is the sum of lengths around the loop. Okay? That's also known as the circumference. Which is also known as 2 pi r. All right? So that's the value of this integral. It's just 2 pi r. So what we get is mu naught I z hat over 4 pi r squared times the value of the integral, which is 2 pi r. So then we can simplify. So this factor of r cancels out one of the factors of r in the denominator. The pi cancels out. The 2 cancel. 2 and the 4 partially cancel. And so what we get is that the magnetic field at the center of the circle is mu naught I over 2 pi r. Oh wait, 2r, excuse me, times z hat. All right? So that's for a full circle. All right? So that's kind of cool. Basically what it says is more current means bigger magnetic field, and a smaller loop means bigger magnetic field. All right? So there you have it. So my next question for you is, well, what if we didn't have a full circle? All right. Well, if we didn't have a full circle, let's say that this is the center, and instead we only had a circular arc. Okay. So it's basically like a slice of pizza here. And that circular arc takes up theta radians. Okay? So it has current. You could go through the calculation. And by the way, this doesn't really make sense just by itself. You'll see once I put it all together, it'll make sense. But you can't have current just appear out of nowhere here and then vanish there, right? It has to, the wire has to continue. But let's just say we wanted to calculate the magnetic field. So there's other parts of the wire that's out here. But let's say that there's a circular arc and we're trying to calculate the magnetic field at the center of that circular arc. Then the calculation goes through exactly like it did before, okay? You can double check it. There's no part of this calculation where we said anything about it being a full arc except for right here, okay? So this is the sum of the lengths around the loop, which is the circumference, which is 2 pi r. But because we don't have a full loop, if we don't have a full circle, this would be the sum of the lengths around the arc, which would be the arc length, which is just going to be theta times r. So that so the length of that arc is theta in radians times r. All right, and that obviously works if you have a full circle, because a full circle is 2 pi radians, so you get 2 pi r. All right, so if you plugged in theta r right here, if you plugged in theta r, what you would get is you would get that the magnetic field at the center for an arc is going to be mu naught I times z over 2r times theta over 2 pi. All right? So this is basically the fraction of a whole circle you have. All right? So if you have half of an arc, you would, if you have half of a full circle, you would take this answer for the full circle and divide it by 2. If you had 60 degrees worth of an arc, 60 degrees is a sixth of a circle. So I would take the result for a full circle and divide it by 6. If you have a quarter circle, you'd take the result for a full circle, divide it by 4, etc. Okay? So that's really useful because we'll be doing problems with circular arcs. So there's another important fact. So suppose I have a straight segment of wire. All right. And I want to calculate the magnetic field like right here. I'll call that P1. Or what if I have a straight segment of wire and I want to calculate the magnetic field here at P2? Well, let's take a section of the wire, okay? And its dl vector is going to point to the right. And then its r hat vector is going to point also to the right. Okay? So what that means is that the angle is 0 degrees in this case. All right? Here we have our segment of wire has dl going to the right. And then our r hat vector points from the segment of wire to the point P. So it will point in the opposite direction. So here we have theta equals 180 degrees. They're anti-parallel. But here's the thing. Sine of 0 degrees is 0. Sine of 180 degrees is 0. So both of these are going to have dl cross r hat equal to 0. Because the magnitude of dl cross r hat has that sine theta in there. Okay? And if it has 0 magnitude, it's equal to 0. And here's the thing. The magnetic field is the sum of over dl cross r hat. So if dl cross r hat is 0, then we're adding up 0. So we're just going to get no magnetic field. So what the important fact is that there is no magnetic field directly in front and directly behind a straight wire segment. So let me show you how to sort of like synthesize all this together. Okay. What if I had a loop of wire that was like really weird? Okay. So maybe it looks like this. Something like that. Okay. So what we have are two semicircular arcs, but the semicircular arcs have different radii. Okay, so this one has a radius r1, and this one has a radius r2. And then we have two straight line segments. So this shows why we have to know the magnetic field for a circular arc, because even though this is a loop of wire, it is made up out of circular arcs and straight line segments. Okay. If I wanted to know what is the magnetic field at the center, it's going to be the magnetic field from the top arc plus the magnetic field from the bottom arc plus the magnetic field from the left segment. When I say left segment, I mean that one, plus the magnetic field from the right segment. And if I look at the center is directly behind the left segment. So the left segment doesn't make a magnetic field right there. So I can cancel that out. And then the right segment, the center is directly in front of it. So the right segment doesn't make a magnetic field at the center either. And so that is 0. So really the only two parts of this loop that are creating a magnetic field at the center are the two circular arcs, semicircular arcs. All right. So you can solve sort of like weirdly shaped loops by knowing the magnetic field of an arc, and then knowing that there's no magnetic field directly in front or behind of a straight wire segment. So that's a useful fact. All right. So that is my lesson for today.